As so often, this tutorial started out with a question by Edward Sikharev. Sorry for maybe butchering your name there. So Edward pointed out this image that his wife made, and he asked if there was any procedural way of creating those disco ball patterns, which his amazingly patient wife apparently placed manually in this image, which results in an extremely good tiling, however is also a bit labor intensive. And he also sent images along like this, so a very disco skull, and an image of this, a horse made of keycaps by an artist called Bobby's Cloud. And what all of these images have in common is that they have this tiling, this topology of square rectangles. And when looking closer at images of the skull or this horse here, you can see that while in most areas this tiling, the topology, fits the geometry, the underlying geometry really nicely, in some areas here, where you have creases, or here, where you have a few quote-unquote lines of the topology meeting, you're getting issues. You can see that in this skull a bit better, where you're clearly getting issues in those areas here, or maybe here, where the underlying skull comes through. And that's just in the nature of these tilings. So I was thinking, what would be an easy, clever, and approachable way of generating those tilings? And as luck would have it, I thought about SideFX's lab tools. A really great toolset implemented by a few SideFX guys around, Louis Corel and Paul Ambrosiusen, which you'll find up here, and if it's not up here in your toolbar, just add it to the shelves. It's called SideFX Labs. And if you haven't installed it, just hit update and it will install. Quick disclaimer, in a few 18.5 versions, the installer didn't work, so that's why I regressed to the 18 version here. However, with the current Houdini updates, it should be fixed, I hear. Doesn't matter, as we're not using any Houdini 18.5 specific nodes, so it can be done in 18.0 as well. And we'll be using a very clever and special node in here, which is called Instant Meshes. Instant Meshes is a free piece of software created by Wenzel Jakob to demonstrate a paper on quad remeshing. And Instant Meshes is really good at generating these isotropic quad meshes, which means we'll get a mesh that consists out of quads only, and it tries to keep this quads as quadratic, as rectangular as possible. So let's create this setup by in Houdini dropping down a geo node and diving in there. And in here, loading in two files, which I prepared by just dropping down a file node, clicking here, and then make sure I uncheck show sequence as one entry. In this case, I think I saved it as a bgeo. And yeah, one is a dog head that I prepared by just downloading a 3D scan from 3dscans.com and just cutting out this dog head here. And let's drop down another file node. And in here, I want to select a piece of geometry that my dear friend and extremely talented artist, Cornelius Demmerich, prepared, which is a bunch of keycaps. So in here, what looks like one single keycap is actually, if we middle mouse on this, we have a path string here. You see 20 unique paths. This is actually 20 different, slightly different keycaps, just being at the same position and thus overlapping. All right, let's work on the topology of our geometry onto which we want to instance those keycaps first. The first thing I want to do is smooth this out a bit so the most prominent creases get a bit less prominent, which helps in the tiling. Remember this skull here, for example, those areas where we get overlaps in the mirror plates become an issue. So let's try fixing them or smoothing them out a bit by using an attrib blur, which we attach to our dog's head. And you can see this smoothed out the mesh a tiny bit. Next, let's create this quad mesh by using the SideFX Labs Instant Meshes node here. So that mesh goes into the first slot. Let's highlight it. And you can see immediately we get this nice quad mesh topology. And you can see that even in those areas here, which looks a bit more triangularish when we enable the points, you can see that even those polygons here are quads. So every single polygon in this mesh now, as it's set up by default in the Labs Instant Remesher here, is now quad, which is good. Let's increase the target polygon count here to give a bit more quads here and a bit of a finer tessellation. In our case, let's maybe set it to 3000, and you can see it's already looking a bit more detailed. You can influence the direction and the layout of this quads a bit using the crease angle. If we increase that here, you can see the layout changing a bit. And I found the layout with a crease angle of 90 really nice. And I increased the smoothing iterations a bit to smooth out those generated quad topology a bit better. So that's what I'm gonna go with. And as I want to copy those keycaps here onto those individual quads here, for each of those quads I want to generate a center point, which will be the point onto which I copy those keycaps. And later I want to dial in those center points Pscale value that determines the scaling of each keycap that we're going to copy onto those points. So let's create the points first. I'm going to do that using a bit of vex in a primitive wrangle. And in here, for each primitive, I just want to add a new point into our current geostream, one with the ID 0, that's the first slot. add our primitive's position, which will be equal to the average position of the primitive's corner points. So that's just accessible via v@p. And now you can see I added those center points here, and on some quads you can't see them as they are slightly below this quad here. Okay, let's also add these newly created points into their own point group, and for that I need their point number. So let's call it this int new pt. So into our variable new pt we're storing their respective point numbers, and now we're just calling the set point group function, telling it to work on our current geostream, create a new group called new, and into it let's add our new point and set the group relation to be 1, so it's in that point. So now if we middle mouse on this, we can now see we've got 2,975 points in that new point group here, which are the center points. Next, to orient our copies, let's just demonstrate what would happen if I would put a copy to point straight down here and just wire in our center points. Make sure we're selecting the new group as our new target points and pack in and instancing our geometry onto the mesh, so that makes it a bit more performant. And then the keycaps go into this slot, and let's highlight this, and you can see the keycaps are very big. So to fix that, let's use an attrib create, which will wire in between the primitive wrangle and the copy to points. And we want to create a point attribute called Pscale, which copy to points will automatically use to scale my keycaps here. And let's set it to a value of maybe not 0.1, but 0.03. And you can now see that on the one hand, we are getting those placeholders here in the distance to make the viewport a bit more performant. On the other hand, you can see that all the keycaps are oriented in the same direction. In order to fix this display issue here, we can hit D over the viewport, go to the Optimize tab, and then set the scene polygon limit to something higher. So now our viewport is a bit less performant, but we can see more of those instances. I'm just going to reset that to my original 20 millions to keep everything performant. So that's that. Let's work on the orientation of those keycaps here. The first thing we need is a normal. So if we highlight those points here and switch on normal display, we can see only the intrinsic vertex normals that Houdini generated internally. However, to get point normals in my primitive wrangle where I generate those new center points, let's just use the set point attrib function to create and set that n, it's a normal attribute, on my newly created point, and it should be equal to the intrinsic normal of the primitives that I can access via v@n here. And of course, this should not read set point group, but set point attrib. So now we can see all our primitives turned black because they have wonky normals now. However, the point normals in our new group just work fine. Right, let's highlight copy to points again, and we can now see, well, these keycaps are oriented somehow. And one thing is they definitely should not point in this direction, but should stick out of the mesh. So after the file here, let's use a transform node and rotate those keycaps 90 degrees around the x-axis. So now they're sticking out. However, and let's just ghost the underlying mesh, they do not really follow the direction of the edges of the individual quads. And to fix that, I also need to provide my copy to points with an up vector, so a second vector, which tells my copy to points how to rotate those individual keycaps. So to generate an up vector, we are looking at our quad, and we can see our normal sticking out of that center point of our quad. In this image, it would just come out of the screen here, pointing towards us. And we've got those 4 edge or corner points of the quads, and we want to use our quad's geometry, that means one of the edges, to generate an up vector. In this setup, I just want to use the first 2 points positions, so I want to get this vector here. And I can do that by just subtracting the original position from the end position here, like this. And after I've done this, all I have to do is normalize that vector, that resulting vector, meaning I'm going to scale it to a length of 1. So let's do that in our primitive wrangle here, by first finding out the edge points of our quad we're currently working on, which is going to be a list. And in our case, we know that each quad has 4 points, so it's going to be a list of length 4. Let's create a list. Let's call this one npts. And we want to fill it with the points of our primitive, which can be retrieved using the primPoints function here, which is going to operate on our first geostream. And we want to retrieve the points of the current primitive we're working on. So the current prim number is at primnum. And now we could either use a loop, or as we're just plainly looking up the first 2 points, let's do it manually in this case. So I want to get the first 2 points positions. Let's create a vector, call this one P1 for position 1, or let's call it pos1. And it should be equal to the points position, which is stored on the first point in our list. That's npts 0. Let's just copy and paste this line and also look up pos2, which is our second points position here. Now let's create this up vector. And it should be pos2 minus pos1. And finally, I want to normalize this like this and store it on our newly created point. So just copy this where I set the normal on our point, and let's just switch it out, call the vector up, and in it store the up vector we just calculated. So now you can see all those keys orient themselves along the direction of the underlying quads. Next, what I could do, and let's find an area where it becomes more apparent. So maybe let's look at this area here, for example, where we have 5 quads colliding. And I could try dialing in my Pscale value here, just manually and uniformly, so that each and every keycap has the same size. And I could try matching, for example, now those 5 keycaps here, like so. However, you'd see we're going to get intersections in those areas, and especially in those areas down here where the quads just are smaller. So let me scale that back so you can see those quads down here are way smaller than those quads up here. So instead of just giving these keycaps uniform scale, what I want to do is calculate an individual scale per quad for each of the keys here. And I'm going to do that by finding out the average distance that my center point has towards those edge or corner points in the underlying quad, which I want to store in my variable called avg_dist, average distance. So to calculate the average distance, I'll have to go through those 4 corner points and calculate their distance from the center, which for the first point would be the length of this vector here. Luckily, Houdini has a function for that called distance, so we can calculate just the distance between the center and position 1, which in this example would be 1.2, and we just store this into our avg_dist variable here, measuring the second position to the center, 1.3, and now we're adding this to our avg_dist here. Likewise, we do the same thing for the third position and add this value into our avg_dist as well. And finally, let's do that for our fourth position and add it to our avg_dist. And finally, as a last step, I have to take this avg_dist value, which just now is the sum of all the distances, and divide it by the number of edge points. In our case, that's 4 edge points, resulting in 4.8 being divided by 4 and an average distance of 1.2 for this case here. Let's do this in our primitive wrangle. I first want to initialize my avg_dist to be 0 initially. And then I want to iterate, I want to loop through all the points in this list npts using a for each loop. And in this for each loop, I want to create a new variable, call this one npt, and in it we're going to store current entry that's in npts. So this loop will run 4 times, looking up the point numbers stored in our list npts one after another and writing the point number into npt here. So now we want to create a new float, call it myDist, and it should be equal to the distance between our current center point that we just created via p and this position, this point's position here. Let's call this nppos. And before we are piping nppos in this function here, we have to look it up. So create a vector, call it nppos, and it should be equal to the point's positional value stored on npt. So after we looked up this point's position and calculated its distance to the center, let's add it to our average distance. So avg_dist plus equals myDist, semicolon missing here. And now finally, after we exited that loop, we could either divide this avg_dist by 4 and rely on our instant meshes here taking care of every primitive being a quad. However, if we mistrust our instant meshes, or if we for some reason want to feed primitives in here that are not a quad, let's look up the number of points in here by just calculating the length of our list here using our len function and casting it or storing it into a float. And now finally, let's divide our average distance by our number of points. In our case, this should be 4. And finally, write it out as our Pscale value. Now to have an effect, let's just disable the manually set Pscale down here. And we can see that's a bit too big, and that might be because our keycaps are generally scaled very large. And that for some reason still does not look right, so let's try finding and fixing the issue. And in order to fix this, one thing I want to do is take care of that issue why we're seeing all those bounding boxes here. And that is due to the fact that Houdini tries to limit the polygon count of this scene. And you wouldn't think that the polygon count of the scene is so big. However, what I mistakenly did in here, after I brought in those keycaps that Cornelius modeled here, is I'm bringing in all of those 20 individual keycaps, resulting in lots of polygons and lots of vertices. And currently I haven't taken care of instancing only one keycap onto one point. So when I middle mouse on the geostream with the keycaps, I can see I've got a variant attribute on my points here. And when I go into the geo spreadsheet, I can see that my variant attribute ranges between 0 and 19. So that's an attribute I created used to keep apart the individual keycap geometries. And to just instance one single keycap onto one point, I want to head over to my copy to points and check piece attribute here, which is already set to variant, and then highlight this copy to point here. And now you can see an error message here from the copy to points, warning me that the piece attribute, which is specified to be called variant, is not present on my input here because I didn't create it yet. So let's take care of that by adding a point wrangle, which we're going to run only over the new point group. And in here, we want to specify an integer called variant, which will live on our points. Now let's just use the random function, seeding it with our current point number, plus a seed that we'll be able to dial in with a slider here. And we want to multiply this number by 20, so it lies between 0 and 19. Now we can see we have all these different keys instant correctly onto our dog mesh. And also now the display errors are gone. So down here you can see those individual keycaps aren't really influenced by our Pscale value that we set. And that is because up here in the primitive wrangle where we created this Pscale value, I accidentally set the Pscale value onto our primitives, not onto our newly created points. So let's just copy this line up here. And instead of this f at Pscale, let's use the setPoint attrib to set that Pscale to our average distant. We just calculate it, and we can get rid of that here. So now all those points are currently very small, because while trying to find the error, I dialed back their uniform scale. So let's reset it to 1, and we can now see that those points are scaled according to the size of their quads. Now we can use that uniform scale here to dial in those individual keycaps so they kind of pack nicely. And you could say that for most applications, this already is sufficient. However, there is one particular area in meshes that can cause issues. Let's, for example, look at this area where the ear is close to the dog's head. And you can see in the underlying geometry, when I highlight this, we've got creases here. So those areas kind of fold over each other, which when we copy and instance keycaps on them, result in those intersections. So ideally, what I want to do is two things. First, I want to find out quads which have kind of an irregular shape and not use them to put keycaps on them. For example, here you could see those areas in here are kind of wonky. And I could either write a bit of vex code to measure the angles of their edges and see if they are rectangular, or in this case, an even simpler approach, which I found working quite nicely, is to take this mesh here and use a measure node. Wire this in here, highlight this and maybe highlight the node's handles here, and measure each primitive's area. And you can now see that the primitives with a smaller area, the area in blue, are those which are not as nicely or not as easily suited to use them to create those instance points here. So let's just take this area attribute here, wire this into our primitive wrangle, and in our primitive wrangle, down here where we create those template points, before we do all this, let's check if the area we stored on the primitive is bigger than some threshold, which we're going to look up using a slider. Call this area threshold. And only if the area is bigger than a set threshold, then let's execute all this down here. Let's just indent it. Let's create our threshold slider here. And we can see that this is very sensitive because the area values are very small. So let's head to our parameter interface. Edit the parameter interface and let's set the upper range of this to something rather small like 0.02. Apply and accept this and see we can now dial this in a bit better. And yeah, we can. So with this, we can now drive onto which primitives I'm creating those instance points. And I think I'm going to dial in the interface a bit further. 0.005. Let's apply and accept this. Yeah, that's better. Okay, let's have a look at the effect of this by highlighting the copy to points and then increasing that threshold. And you can see we're thus isolating areas where there's very little room to instance new keycaps onto. Another thing I could do and I want to do to prevent those intersections is offset instance points which lead to those intersections here. In order to demonstrate what I mean, let's look at this example where we have those two creasing primitives, those two creasing quads, and at their center we already generated those center points. One has the point number 17, the other has the point number 73. And to find out if the geometry that we'd instance on those points would intersect, the first thing I want to do is move those points outwards a bit along their normal, like this, so they now kind of float above their parent quads. And next, for each point, I want to search for points nearby within a given radius. In this case, searching from point 17, we'd find point 73. And we could now just say, we simply, without checking anything else, move point 17 back to its original position and down a bit and push it in to de-intersect. However, as we're running this in parallel, searching from point 73 would also result in a point being found within this radius here, in this case point 17. So if we did not do any checks, we could also now move 73 back to its original position and back a bit further to de-intersect. So we'd now have moved both points. However, to de-intersect those keys, we usually only need to move one point. So what we also do is we check if the point from which we searched has a bigger point number than the point we found, then and only then we move that point. In this case, resulting in only point 73 being moved, first back to its original position, and then a bit along its normal, so a bit into our geometry to de-intersect. Let's code this up by dropping down another point triangle, which I want to use to store a point's rest position, and should only run over the newly created points. So v at rest equals our current point's position. So we're just going to store those center points' current position here, because we're going to need that later. Also in here, I want to offset those points a bit. So let's set our current point position to be equal to our current point position, but to it, add the normal, in this case resulting in those points being pushed apart 1 unit from the mesh, which is a bit too coarse. So let's multiply the scale of this normal by our current Pscale value. So now these points are only being pushed out by the Pscale attribute stored on those individual points, and we want to decrease this further by just halving it, so multiplying it by 0.5. And just to be explicit, let's write it like that. So now we just pushed those points above the mesh a tiny bit. Next, let's drop down another point triangle, which goes in here. So in here, the first thing we want to do is specify our search radius, which I'll call red for radius. And let's use a float slider to dial that in. Call it search radius. Let's also adjust this parameters interface to be between 0 and, let's say, 0.1. We don't need much here. The mesh and the distances are pretty small. Next, let's find the points around our current center point. And by the way, we need to make sure that this is running over our new points only. So to find points nearby and to store it into a list, let's call this list npts. We're going to use the near points function, searching on our current geostream around our current point's position, and we want to find points within radius rad, and we only want to find the 2 closest points. Why do we want to find 2 closest points? When using near points, for example, from this point here, point 17, we're going to call near points using this point's position and trying to search for points around this position, like this here. In this case, as we're disregarding the point numbers in that near points function, this will return 2 points. The point from which we're searching itself, because it sits exactly on the position from which we're searching and within that search radius. And this point here, which is not exactly on the position, but within that search radius. So in order to get this point here, we not only need to find the very nearest point, which would be the point from which we're searching itself, but also the second nearest point. So that's why we're searching for the 2 nearest points, not the single most nearest point. However, as we don't need the absolutely nearest point, that is the point from which we're searching, we can directly remove it from that list using the remove index function. And from this list, so from npts, we're going to remove the first, that is the closest entry, the one with the ID 0. After that, we want to check if our list contains any entries still, or if we just found the single point from which we're searching. So let's create a variable called no for number, and should be equal to the length of npts that remains. So in the optimal case, this should be 1, and if we didn't find anything, it should be 0 now. So if there's still something in our list, so if no is bigger than 0, we want to set our point's position to its rest position, the original position on the quad, minus its normal. Remember, we wanted to offset this a bit into the quad, minus its normal times, let's use a float slider and call this one offset. And let's also multiply in the average size of each quad, which we stored in Pscale. And if our list is 0, so if we only found the one point from which we're looking, then we want to set point's position to its rest position. so its original position on the mesh. Also up here, we want to check if not only our list has an entry, but also if our current point number is larger than the number of the point we found, which is stored in npts 0, the first entry. All right, let's create that final missing float slider with the offset, and let's slowly increase the search radius and also the offset. You can now see some of those points disappearing, and if I highlight my nodes correctly, like so, you can now see we are pushing those points in or not. Let's have a look at this effect with the copy the points highlighted. And up here in the first primitive wrangle, let's dial back the area threshold so we're not deleting anything by area. But down here, where we're offsetting this, maybe I want to color code this because this is one of the important nodes. Let's set the offset to 0.4 and slowly increase our search radius. So now we're pushing some of those points close by into the mesh and thus getting rid of those intersections. And that is what I'd call an acceptable setup. It's not 100% perfect. It might need some manual adjustments, deletion or rescaling of one of those keycaps or a few of those keycaps, but it quickly enables you to pack a mesh with almost uniformly scaled rectangular or quadratic objects, such as keycaps or those tiny mirror plates that make up a disco ball. Finally, let's just get rid of this attrib grade down here with the Pscale. We don't need this anymore. And let's just clean up our setup a tiny bit. But that is it. So most of the heavy lifting is done by the instant meshes, which again is a really handy SOP to have, and in itself a very good reason to install and tinker with SideFX Lab tools. And you know the drill. I'm looking very much forward to all kinds of artworks you folks out there create. And if you want to support us and in the process learn more about Houdini and maybe a tiny bit of Unreal, you might want to consider supporting us on our Patreon. And to everyone already supporting us, thanks so much. It is through your support that we are able to do what we do. And a very special thank you goes out to Important Looking Pirates, Patrick Fillion, Chris Hebert, and Rafik Anadol. Thanks so much, folks. So, until next time, it's cheers and goodbye.